Раз, два.
Europeana, la estrategia nacional vigente de 2020.
А-
Алло.
Алло, алло.
Раз, два, три. Слышно что-нибудь? Раз, два, три. Алло.
Я ничего не
Ай.
слышу что-то.
Раз, два, три. Раз,
Сейчас,
два,
может
три.
быть,
У меня что-то не так?
ничего не слышу. И пока никого
Раз,
нет. Вот.
два,
А
три.
вот, все
Раз,
слышу.
два, три.
Сейчас слышу.
Вот. А
Вот.
мы разослали объявление?
Да, я не знаю. А
Сейчас я
Гач меня
проверю,
спрашивал, типа, это когда будет там. Говорю, вроде с точки зрения Гача разница между Парижем и Москвой 2 часа. Я ему написал, что
Нет,
вроде бы разница 1 час.
1 час, да. 17:30 Пэрис.
Да. А что-то
Стайн.
никого не.
Ну, это самое еще рано.
Никому это не интересно.
Одиннадцать
Нет.
тридцать это самое в Гаче должно быть.
Так. Да,
Нет,
11:30.
если
Я
мы
вот.
хотим привлечь Лорана, то, наверное, и всяких французских товарищей, то при этом сохранив возможность для
Надо
американских,
пораньше.
нет, надо позже, потому что... Нет, если раньше, то Гачи не сможет это самое зайти. Значит, сейчас как раз Лоран должен ходить за своим сыном в детский сад и отвозить его домой, поэтому вот это конкретное время ему как раз максимально неудобно. Но ладно. Сейчас уж назначили. Значит, я вроде договорился обсудить сегодня с этим самым с Юрой Кудряшовым чудеса в решете в виде чат GPT. Вот, но пока что я его пробовал
Для чего?
для разных вопросов. Ну, там, в каком пакете определяется латех команда там какая-то. Или что нужно загрузить, чтобы в питоне был пакет Network X или что-нибудь еще. И он очень хорошо все отвечает. То есть пока его советы оказывались вполне действующими.
Например, есть такая тема, дать ему подумать или нет.
Да, но, кстати, я его
Например,
просил составить библиографию для работ Вьюгена, и он придумал совершенно несуществующую работу. И указал журналы,
ну
все
это да,
такое
это
там,
может
да.
быть.
А зато китайский DeepSeek, он
Ну, я
более...
говорю, потом после Кудряшова можно послушать более технический вопрос, как это работает на техническом уровне, как это все определяется формально. Вот.
Мгм. Нет, но Кудряшов
Как
тоже,
там все
наверное, знает,
генерируется.
как это все делает. Но нет, но это было бы очень хорошо послушать. Ну, если человек реально в этом участвовал, это, так сказать, знает, как это все, то это очень здорово.
Не, ну даже я так условно знаю, но я никогда это не, ну, так руками не программировал ничего. А вот человек прям программирует бесконечно. Это все, там разные
Да.
эксперименты там с этим делает.
Да. Я без разговоров с Кудряшовым подготовил разные вопросы. Но вот пока люди собираются, можно их обсудить. Что его еще
Да.
надо спросить? Первое, что происходит, когда мы задаем задачу? Есть ли какие-то этапы, перевод, трансляция на какие-то формальные языки, запуск каких-то программ, поиск веб или вообще что-нибудь? Второе, ситуация с формальными пруверами типа Лин и Кок. Значит, в каких они формальных системах работают, как это связано с классическими системами типа пиановской арифметики и ZF, и, значит, и в какой степени где сейчас проходит граница, что можно формализовать и что можно автоматически формализовать. Третье. Насколько вообще это все искусство? Вот в разных странах есть разные эти самые чат GPT, и it seems that there is more than it's just is there some kind of secret things or somehow everything is known and you need just to find more data and more things. And fourth, what was exactly the competition without International Olympiad, and what was allowed and what was not allowed, and so. And fifth, is there a chance for a modern system, GPT, to learn some theory from a book and then solve exercises? Or they need much more data for learning? And sixth, whether the theoretical results about machine learning was useful or irrelevant. And so we are trying to
Irrelevant,
invite some
I can
person.
tell.
No, but for you, they're very relevant, and the question whether are relevant for this. So we have a friend who worked in a company
No, I'm saying that
which
they were irrelevant in the development of ChatGPT. All this stuff that I'm going to tell you now was completely irrelevant.
irrelevant, yeah. But what I want, what I'm trying to say is that we will trying to invite a friend from the ChatGPT, not ChatGPT, but one of these companies who solved the problems for International Mathematical Olympiad, and I hope he can answer our questions and try to explain this miracle, how it works, how it's possible, and why this obviously impossible thing somehow works.
Yeah, and please ask the question number 0. Where does he work?
No,
In which company?
Yeah, I think he will answer it independently. But probably he is not allowed to speak about his companies, but he can speak about the other companies, what they are doing.
Yeah.
So if there are some questions which you would think it's useful to send to him in advance, just send them to me, and I can forward them to this guy.
Can a machine think?
No. This is one question which I want. This will
Yeah.
attract philosophers, and this will be the end of things.
Yeah.
Okay, so there are also before you start, there are
So
some.
are we trying to wait for Vereshchagin?
No, there are bad news and good news. Bad news that Vereshchagin is ill he just is undergone the operation of changing the sustav. I don't know how to say it. Тазобедренный сустав, changing the joint, and this is quite complicated operation and so on. And this is bad news. So he's still lying in the bed mostly, and on only one side, because the other side is forbidden for him. But the good news that things seem to be improving now, and there are no complications yet. So he will be even able to come, but this I don't know.
This is nowadays. This is generally a very developed and successful operation. I just had one of these in the summer, and I have recovered from it.
Yeah, but he has in August, so you are in a better position. Yeah, and also you have done it in Boston and he in Moscow, so this can be also a difference. Yeah, but I hope not.
Yeah, I hope everything will be fine.
Okay, so let us start our first meeting in this new academic year, and our leader, Monsieur Kozachinskiy, will give a talk.
Yeah, I just wanted to apologize. I will have to leave before the end because our seminar starts here.
Yeah. Okay.
Okay, I'll try to share something where I can write, but nobody else can. But I guess that's fine. If you want to say something.
Okay, but now we can. Yeah.
And maybe I can even write. I can write hello.
Yeah, and this is recorded. So if you don't want to be recorded,
please leave.
I don't know what we can do. Yeah. Okay, it's automatically recorded, and Misha Raskin will have that.
Yeah, so I want to talk about dimensional networks, but I guess let's let's recall some basic things. So, yeah, sorry, I also have to.
Yeah.
So we will VC dimension can be measured over what is called the concept class. So if I have a set X, a domain, we can have now a concept class which consists of some functions from X to 0, 1. So let's say we can write it like that. A concept class. Yeah, so let me define two things. So I want to define M sub H of N is the maximal number of functions, I forgot, maybe I write wrong, functions realizable by H on a n element subset of the domain.
Yeah, if I remember correctly, you're especially interested in the cases when all functions are realizable.
Yeah, so we can note that obviously mh of n is at most 2 to the n, and so well, you can define now also the VC dimension of the class H is the maximal D such that mh of D is equal to 2 to the d. So, so basically you are interested in the maximal d such that there is some d element subset where you can realize all functions. Right? So maybe I can ask some question about that. So let's say that I have mh of d is less than 2 to the d. Why this implies that mh of d plus 1 is less than 2 to the d plus 1. So this is a question to the audience.
Yeah. So just please answer someone. No, it's not I guess it's not a difficult question because even I think I know the answer, but still, just to make, just try to let anyone else try to do this. Do we have some people who are alive?
Yes.
Yeah. So Peter, of course, it's not supposed for you, but let's try. You can also try if no, there are no volunteers.
Oh, you mean there is some other audience that is more an audience?
No, okay, yeah. Just no, there are some recent students or students. They should be the most clever part of the audience, so they could try to.
Okay, let me give.
Repeater, you are muted
Yeah,
if you're...
you're muted. Yeah.
Generally mute myself. Yes.
Yeah. No, I think even a stronger thing is true that mh of d plus 1 is doesn't exceed 2 times mh of d.
mh d plus 1 is upper bounded by 2 times mh of d.
Yeah.
Because, well, we have to bound somehow the number of functions we can realize by h on any d plus 1 element subset. So we have d plus 1 elements. We have to bound this number by 2 times the maximal number of functions we can realize on d elements. So how do we say that? Oh, well, I guess let me just say it because maybe it's just too obvious to tell. So it's just, well, okay, let's take this. We have these d plus 1 elements. Let's just for a moment throw away one of them. So we only are left with d. So on this d, you can have at most mh of d functions. And each of them you can extend at most 2 ways. Right? So that's it. So it means that if this is less than 2 to the d, then this is less than 2 to the d plus 1. And this means basically, this is regard with this definition of VC dimension. So it means that in the beginning we have some number of, well, we have mh of 1 is equal to 2 to the 1. Then we have mh of 2 is equal to the 2 to the 2. And so on up to the VC dimension, which is, let's say, d.
Of d.
And, oops, yes.
mh of d.
Yeah, and then, well, and then they all starting be smaller than 2 to the d. So d plus 1 now is smaller and so on. Well, it can be the option that it's like infinite, BC dimension is infinite, then it's just 2 to the d for every d. But if it's finite, it means then it's 2 to the d up to some d, and then it's strictly less than the corresponding power of 2.
And if I remember correctly, there is something called Zauer lemma, which says
Yeah, so
that
we will need this
grows,
lemma.
yeah.
So we will need that lemma that, I mean, okay, so one option is that when it's, so one option is when it's finite, then it grows like powers of 2. This, well, I mean, then it's
Infinite.
Oh, sorry, so when the we see of h is infinite, then the sequence
Is just exponent. But if it deviates at some point, then it grows, starting from this point, it grows
and it grows just
slowly.
polynomially.
Polynomial, yeah.
With a degree of a polynomial that depends on d, but okay, let's even like, okay, then it's just 2 to the n, and then there is a lemma of Zauer-Schilach lemma, or whoever proved it first. I guess somebody can say that Vapnik and Chervonenkis also proved it, but usually now it's called this, Zauer.
No, it's not Zauer, but Zauer, I guess. So
Sauer.
Schelach is without K. Okay.
Yeah, well, I don't know.
Yeah.
Sorry, so for not preparing my talk. So basically, the lemma says that M for any H such that of VC dimension D, finite. Well, you can even formulate it for any D, but then you basically have MH of N, the maximal number you can realize on n elements is bounded by the sum of polynomials. Binomials n choose 0 plus n choose 1 plus up to n choose d. Well, if you, even if d is infinite, you can interpret this sum as just the infinite sum where just up to the n choose n, right? Then it will be just 2 to the n. But if d is finite, then I guess you can bound it by something like this is at most n plus 1 to the d, right? So, okay, we can try to prove it, maybe. Well, we have seen.
Yeah, last year we have seen it. I don't know, but if it's short, maybe you can try.
Yeah, well, okay, let's try in any case. So it follows from the lemma. Okay, the lemma says that any hypothesis class on a finite with a finite domain, let's say y, shatters. I will explain. I will remind what shatters is. At least as many subsets of y as there are functions in the concept class. And shatters so basically we want to say that H shatters some set S means that H can realize all functions on S. And then we can say in these terms that we see dimension of the class H is the maximal subset, size of a subset shattered by H. So far what we have done, we have formulated the notion of shattered. We have noticed how to formulate VC dimension, how to define VC dimension in that terms, and we gave a lemma that every hypothesis class over domain Y shatters at least size of H subsets of Y. So are there any questions up
But
to
it
this
can
point?
shatter much more subsets.
Sure. It can shatter all subsets, let's say.
No, for example, if we have H, which consists of 0 constant and 1 constant for big Y, then it shatters all one-element subsets.
So if we have all 0 function,
so if we have only 2 elements in H,
all 1 function, yes, sure. And then if we have, I don't know, as Y is the set of the first n, well, I mean, from Y is the set of numbers from 1 to n, then this H, well, we can actually try to understand which subsets, how many subsets H
just
such.
every one-element subset is shattered, if I understand correctly the definition.
Yes, every
So
one element subset, well, I don't know, I have the subset, this subset, it's shattered because I have a function which is 0 on it, and I have a function which is 1 on it. Are there any 2-element subsets of Y that are shattered by H? Shattered by H.
No, I think that no, but
Yeah, sure, because to shatter a 2-element subset, you need at least 4 functions in the class. But in any case, I think you can say that H shatters n plus 1 subsets, right? Because we also count the empty set. It's shattered. Okay, so I hope this is clear. Now, there are 2 things. So, and one thing is why the lemma inside the proof implies the lemma of Sauer-Schilach. Sasha, is you are only one trying to speak? Maybe you can explain.
no, I think imagine that the dimension is small. Then big subsets are not shattered. And
So let's try to write it down.
Only small subsets
Let me try
can be.
start writing it down. So we have an argument that lemma inside the proof implies lemma Sauer-Schilach. Lemma of Sauer-Schilach. So we take any, so okay, we want to show that mh of n. So we assume that VC dimension of H is small, is it, I don't know, D. So it means you're saying that H cannot shatter sets of size
D plus 1.
D plus 1 and more.
And therefore it can shatter only smaller sets. And we know that there are not many of them because just the formula just gives the sum of size number of sets of all sizes.
Yeah, it means that on an element subset of on some n element subset, it can shatter on an element subset Y, let's say. It can
Why you
shatter
say
it.
subset, I don't understand. It's just set.
Okay, set. It can shatter at most. And to the 0, an empty set, one element sets, and so on. The element sets. But on the other hand, by the lemma inside, this is at most, well, the restriction of our class to that. So this is at most mh. Sorry.
It's bigger than
This the number of it can shatter at least
H.
the restriction of our class to y. Well, we can say that we have we can restrict everything to this n element subset and just ask how many sets we can have, how many functions we can have in this class of BC dimension D, which is on the domain of size n. So let's write it like that. And this implies the lemma of Sauer-Schilach.
And then I remember last year, so there was some kind of inductive argument why it shatters a lot of sets. But
yeah, it was
I
induction
get
by
something.
So we want to show that H shatters at least so we have a class with domain X, then shatters at least the size of H subsets of X. I think you can try to prove it by induction. On the size of X. So I don't know, let's say we have just a one element X of size 1, which consists of one element A. So, well, basically you can either have just one function and then you can shatter the empty set, or you can have two functions, then you can shatter the empty set and the X itself, right? So supposedly the induction based is clear.
So the induction is for by X, and the statement is that for all H something is true.
Yes.
So the quantifier is in the statement which proved by induction. Yeah.
So for when X has size 1 and H is 1, that just one function.
So now we should
Then I
increase the
can
size of
realize the
H.
empty set. No, the size of X.
Yeah. So now we increase the size of
Right.
X. Yeah. If
Yes.
your plan. Let's see.
Say we have some set X which has points A1, A2, AN plus 1. Okay. So then what I can do is that I can apply induction to the first n elements. Then I can say, well, okay, I can shatter. And let's consider the restriction of my class to the first 10 elements, right?
Yeah, the H is a union of functions that are zeros on n plus 1 and the function that are 1. And this is the union of these things, two things.
Yes. So what I want to say is that, okay, well, I can shatter shatter at least, by induction, I can shatter at least the size of head H subsets of just the first n elements, right? I haven't used the last element so far. Right, is by induction. But the problem is that the number of restrictions, the size
Is
of
of course smaller
H,
than
it can be smaller, but how much smaller? The point is that there are some restrictions that are only extendable by 0. There are some restrictions that are only extendable by 1. And then there are some restrictions, let's call them H hat 0, 1, extendable by both 0 and 1. Extendable.
So it's smaller because we sometimes count two different elements on from H as one element of H hat. And this means that there are
Yes.
two
So
strings.
basically we have to add at least this many subsets, right? That are shattered. Because I mean the size of this, the number of restrictions that are extendable by both 0 and 1 is how much H is bigger than, the size of H is bigger than the size of H hat. Right? But the point is that, okay, so all this, you can apply now the induction also to this class and to this element. The point is that if you can shatter some subset here by this class, you can also shatter this set with an plus 1, right? Because you can realize anything here and you can extend it both ways to n plus 1.
So what we subtract in one place is compensated in the other place.
Well, I mean, Sasha, there is no even.
Yeah, okay.
I guess you kind of have a remembering some other way to present this stuff, but I'm just
No,
the way
I
I'm
think
phrasing it is
yeah,
a
I
little
know,
bit
yeah.
differently.
Okay.
I just say, okay, I can shatter at least H hat subsets that do not use an plus 1. Then I notice that, okay, how much I need to shatter more. I need to shatter as many subsets as there are restrictions that are extendable both by 0 and 1, because this is exactly an amount how much H is bigger than H hat. And then I just noticed that, well, okay, if I just use this function extendable by both 0 and 1, and they shatter something on the first n elements, I can extend this shattered subset by an plus 1, because everything can be extended both ways. So, and now by induction I obtain more subsets. This more subset, and all of them also have n plus 1, so there are different subsets. Okay, so is it clear?
No,
Or no?
I think it's clear, but we have it last year, and there is even a right notes made for this. So if someone wants, I can send this note, which writes down this argument.
Yeah, okay. So let's get to VC dimension of neural networks, I
Yeah,
guess.
yeah.
So let me try to define neural networks somehow. So it will be some concept class. Let's say a neural network so a neural network with, so we will consider neural networks that output 0 or 1, right? So in order to be consistent, because we want to interested with VC dimension of them. So a neural network with input dimension D, L layers with dimensions d1, d2, dl, and activation function sigma, which is just a function from reals to reals. Well, it's the following concept class. So what you can do, so this is a concept class where the domain.
So the network has d Boolean inputs, yeah?
It has d real inputs.
Real
So
inputs, yeah.
Concept class where the domain is a concept class with the domain is r to the d. So it will be consist of some functions from r to the d, well, in the end to 0, 1. Okay?
So we put d inputs in real numbers as input, and then according to the rules of neural networks, we compute the output, which is Boolean, and so we get some function h, and we consider all the functions.
Yeah, so basically what you can do, okay, you have what they call an input layer. So you have d, it's an input layer, you have on input d numbers. And let's denote this vector, let's say x0. Then you can do some kind of transformation and obtain the next layer. So the next layer has to have dimension d1. So it will have d plus 1 numbers. Let's say, and it will be a vector x1. Yeah.
Strangely, they call what I will call size, they call dimension, but okay.
Well, I don't think there is some very fixed terminology, but
Okay.
in any case, so what you can do here, here you can basically, to obtain x1 from x0, you can do well, let's call it an affine transformation, and then you can basically linear transformation plus a vector. So basically x1 has to be what they usually write sigma times ax0. Well, let's write it like that. A1 plus B1. So what you can do to obtain x1 from x0, you can multiply x0 by some matrix, A1. So the matrix has to be of size d1 times d0. In order to obtain, okay, if d is d0, then the size of A has to be d1 times d0, so that when you multiply a vector of dimension d0, you obtain a vector of dimension d1. And, well, the vector b1 has to be of dimension d1 also. So what you do, you can do this affine transformation, and then you apply sigma. It's what they call an activation function, and you just apply it to every coordinate. Well, sigma is formally a function from reals to reals. Here,
which is fixed for all the vertices of the network, the same function.
Yeah, well, for simplicity, yes.
Yeah.
And you apply it just to every coordinate of the vector. So when I write it like that, I just mean that it's applied to every coordinate. Now, and then this is what they call the parameters, right? So the elements of this matrix and elements of this vector b1 are parameters. So basically, this gives you a concept class. So you can define these matrices in any way that you want. And then for any choice of this, of these matrices, you obtain some, okay, so far you obtain a function from x0 to x1, but now it will be the function. But if you leave the elements of a1 and b1 as parameters, now, this will be just a family of functions or a concept class. So, but in any case, you can continue. Well, you have to do this for L steps, right? So you have this for you have the first layer of the network, right? So I mean, so basically, if you but you can also look at this like that. So for any like what they call a neuron, for every element here, how you compute it? You take the sum of inputs with some weights that are given by the row of this matrix. And then you also have what they call the bias vector. You also add some number. And then to this thing, it's like the input to this neuron, and then there is an activation function which somehow transforms this signal into the level how this neuron is activated or not. I guess I don't know this biological interpretation, but I guess this is something like that.
Yeah, for example, if sigma is an affine function, then we don't get anything. All the functions are affine.
Yeah.
But
So you
if
need
sigma
really a
is something-
nonlinearity here.
Yeah.
So, but let's just continue. So then you have another layer with d plus 2 neurons. So it, and then you obtain the vector x2, which has to be now sigma some other matrix A2 times x1 plus b1, right? And so on. So now this is also the parameters of the network, a new one.
No, I think in your notation it should be B2, but
yeah, sorry,
anyway,
B2.
we cannot
B2,
follow.
B2, B2, B2. And then, yeah, they have to be of corresponding sizes so that from a vector of size of dimension d1, you obtain the vector of dimension d2, and so on. So you have the last layer, the last hidden layer, which has what they call it, dimension dl. And then let's say to compute the final output, which is 0, 1, well, you have to take, let's say, what you can do is that, let's say this is a vector
Just take
x.
some threshold or not.
Yeah, let's take again. Let's allow to take the final output. Let's take some linear combination of. Sorry, it's just Excel. Excel, just the. So the sign of some. Let's take some linear combinations of neurons in the last layer and some number b and compare it with some number b and take the sign of this. Okay?
So instead of sigma, we just use sine threshold function.
Yeah, well, because we have to at this point we have to say something which is whether it's
Yes
0
or
or
no.
1.
Yeah.
So and then the important what are the parameters? Well, the number of layers is already given. L is the number of layers, and then we need the number of parameters. Well, it's just the number of elements in these matrices and these vectors, right? So it will be something like d1 times d0 plus d1. This is the number of parameters in the matrix A1, and b1 is the number of parameters in the vector b1. Then for the last layer, you need dl times dl minus 1 plus dl, and then maybe for the final output you need, well, how many? You need dl plus 1. So it's something like that. This is the number of parameters.
And then there's a general question, maybe you can say something. So imagine we have some function of real variables. Which function of real variables can be implemented in this way?
Well, that depends, of course, on the activation function.
Yeah, no, imagine we are allowing more or less any activation function. Then what? Does the
Okay,
Kolmogorov...
now it's a difficult questions like one. So whether you can.
So, for example, there is a Kolmogorov-Arnold theorem about implementation, everything with one continuous function of one parameter and addition. So, does it mean something for this kind of question?
Well, I imagine that then you. Well, I mean, I never thought about this way. So
There even some kind of sometimes they speak about Kolmogorov-Arnold network. I don't know what it is.
no, it's another thing.
There is something like this. But indeed, we have additions and we have one continuous function. So
Kolmogorov-Arnold network is some generalization of this stuff when you can also somehow choose an activation function, not only the weights, not only the parameters of matrix.
So if you allow arbitrary continuous activation function, then you can get any continuous function or not.
Well, I mean, I don't know. I have to see the exact formulation of Kolmogorov-Arnold theorem. Probably
okay.
yes.
So it's another story. Let's postpone.
Yeah, I mean, if you're saying like that, then it sounds that it should be true, right? But
no, but I don't remember.
My lack of general mathematical knowledge doesn't allow me to answer your question.
Okay.
Right.
Okay.
But so what I was promised to explain, I mean, some kind of natural but not very actually useful in practice case, but some preparation case for more practical stuff is when sigma activation function is also just a sign function. So basically, really you have real inputs, but then all the things here are just zeros and ones, all the intermediate things. And then the idea is that, okay, you can sort of just obtain so what you can do, you can have a neuron that has a signal and then is activated or not, depending on whether the signal it obtains is at least some threshold.
I guess it was more or less one of the first models of neurons and so on.
Yeah, I mean, the problem is that it's not continuous, and then they cannot optimize this in practice, so I mean, it's not very good for the practical stuff. But we can try to at least understand. For example, what is the now most common is this what they call ReLU. ReLU of X is some kind of, okay, so it looks like that. So it just obtains on input a number X, and if it's 0, then it's just 0, and if it's non-negative, it's just X. So far, if the signal is negative, it's just set to 0, and otherwise it's non-negative. I mean, it's just replicates the intensity, I don't know, whatever of the signal. So just maximum of. So then at least it's continuous and like partially differentiable, and then they kind of can optimize this stuff somehow. But, well, you can ask for whatever kind of activation function you have. So what can be the VC dimension of a neural network, I don't know, with that number of parameters and that many layers?
No, so I think now if you can state some result, even if it's difficult to prove, but it's important, just say it.
Yeah, okay. So the first part is that any neural network. So we are interested in the case with sign as an activation function. With activation function, which is a sign, and p parameters has VC dimension, it must P of P times log P. Somehow it's not dependent on the number of layers. And then the second theorem is that how to form. Basically, I want to say that the second theorem is tight even for neural networks of constant depth, of constant number of layers. So I want to say something that for every n, there exists a neural network with sigma as a sign, with activation function sign, with constant number of layers. Let's say with I don't know, omega of n. Sorry, no, it should be where the number of parameters is linear in n, but we see dimension. So here I need to say any neural network with these things has VC dimension, it must this. But here I want to say that for any n, I can construct a neural network with O of n weights and constant number of layers such that VC dimension is n log n. Or better, maybe O of p for every p. I can do this. Let's do it like that. For every p, there exists a neural network with sign activation, constant number of layers. At most O of p parameters, but with C dimension at least p log p.
And when you say O of one layers, that means that it doesn't depend on p.
Yeah. It's maybe 2.
Yeah.
Let's say at most 10. That's for sure. So, but okay. So is the statement of the theorem clear?
So now yeah.
I have a question. The first bound is for any distribution of dimensions if the number of parameters is p.
Yes.
Or yes.
So you're just interested in the number of parameters, and the constant there doesn't depend on the number of layers and distribution of dimensions, all of this stuff.
Mm-hmm.
Yes. So, and then let's try to prove the first part.
No, but is this a classical theorem known for centuries, or it's some kind of new result, or what it is?
So the theorem.
There's a status of
it's basically, well, one is known for the part one is known for centuries. The second part is known for decades. Let's say it like that. So basically, this I don't even know who first observed it. It's some kind of maybe. I can't speculate on it. It's sort of folklore, maybe. This was proved in '94 by somebody named I think that you should spell it like that. So it's like 30 years ago.
Mm-hmm.
But
sorry, there is a natural question. If you change activation function for, say, some arctan or something like this, is it known that the same bound holds?
I can tell something about that. So what I can tell, especially I know what's happening with ReLU. So when I have ReLU, let me state more or less what we know at least. The ReLU, you cannot prove now the same bound. You can only prove the bound which has the number of layers as an additional product. So you can show an upper bound p times L times log p.
Wow.
And this is sort of tight, at least, well, I guess the best known you can formulate it. Well, okay, I can state that at least you know that it can be P times L.
Mhm.
This I also know how to explain, sort of. And even, well,
Mhm.
it's like when P is equal to L. There was an example where the number of parameters is basically the number of layers, and then, well, that happens when basically almost all layers just you have one number.
Mhm. Mhm. Mhm.
And then somebody recently gave some examples where you have some kind of additional this thing which kind of not very okay. So you can have some kind of additional log when L is significantly smaller than P, but still it's kind of not so tight exactly. So let's say when
Mhm.
P is equal to L, you get just P times L, not P times log P. This is a situation for yellow. And then for arctan, the only thing I know about arctan, so well, you can use this arctangents function as an activation function. Well, it should look like that, I imagine.
Mhm.
I only know that basically, if I have a ReLU network, I can simulate it with arctan. And this implies that if I have a lower bound on VC dimension for ReLU, I mean, simulated in the sense that, like, with polynomial blow up in the number of with a linear blow up in the number of parameters and maybe some kind of constant blow up in the number of layers. So maybe I need twice more layers and twice more parameters. And then for arctan function, I have the same lower bound for VC dimension. The upper bound, if I'm not, the upper bound is harder to say. I don't know if they have explicit bounds on the upper bound, but I think it should be known that at least it should be finite for any fixed arctan network. And it somehow should follow from kind of generalization of Tarski-Zeidenberg theorem that you can eliminate quantifiers in the theory of reals when you add exponentiation and all of that stuff, but I have to understand this thing better. But I don't know how to get good upper bounds for arctan, like some explicit.
And for exponent, also, it's
For exponent, well, usually they are like more using this kind of sigmoid, what they call, which is, well, they usually denote by sigma, which is like e to the x times e1 to the e times x. So it looks, well, it's goes to 0 here and then to 1 here. So the only thing I know that the neural networks with that thing have a finite upper bound. So you cannot have any, because for example, there is a standard exercise or something that if you have sine, some kind of function that alternates infinitely many times, so it goes something like that. Then you can just have a single neuron with this thing. So you just can this thing, just let's say sine. If you consider VC dimension of this thing, all the functions that are form sine of sine of a times x, this is infinite. So you have just one input x, you have just one parameter a, you multiply a by x, you take the sine of it, and then the sign, whether this sign is positive or negative.
No, I don't understand. So now the family of function contains only one function, or what?
No, A is parameter vector.
So you take all you take all the all A's, all real A's.
And
Yeah.
actually d-dimensional, as I understand.
No, I mean, to obtain infinite dimension, you just need one parameter. So this is actually like a set of functions from R to 0, 1.
It's interesting, yeah.
So there are sort of things that I can explain now. I guess, well, I can explain this stuff with sinus maybe.
No, but
Yes.
maybe you can explain the old Folklore theorem.
Yeah, okay, so I can try to explain the old theorem. This one. That the upper bound on just neural network with sign.
Yeah.
So let's start to prove the upper bound that if I have a neural network with p parameters, then we see dimension in sign as an activation. So this is just bounded by p times log p. And this is sort of requires a two-step argument. So first I need to consider a very special case. They usually call it perceptron. It's just a concept class where you just have a one input layer. So you have x01, x0d. You just do one linear function. Well, you just take a linear combination of these guys plus some number b, and you take the sign of it, of this thing. So a is from R to the d, and b is just a real number, right?
So we just consider one neuron.
So just one neuron, yes.
Neuron, yes.
So this neuron has how many parameters? D plus 1. So what I want to show is that in that case, so basically I will show that we see dimension of a, let's call it D, this concept class, we see dimension of this class. In that case, I will obtain the exact bound and there will be no additional log, so it will be just D plus 1, just exactly the number of parameters.
So in geometric terms, you have the functions on R to D, and these are just half spaces.
So if D is 2, I
space.
have this sort of functions, right? So like this, oops. The half planes, but not necessarily for half planes that pass through 0.
And indeed, if you have 3 points, you can separate them by a half plane as well as you wish.
Well, at least for not very stupid 3 points. I guess if I take them like that, just on one line, then I cannot separate, I cannot have plus and minus here, right? But if I take 3 points that form a triangle, well, yeah, I can separate any
So
of them.
almost all sets of 3 points are shattered by this family of sets.
Yeah. And then I have to argue somehow that I cannot shatter any 4 distinct points. And usually you can prove it sort of geometrically like that. So if they form, well, there is one case when one point is inside the convex hull of the three other points, right? Then which function
and then
I
you
cannot
cannot
realize?
separate this point from three other points.
Yeah, I mean, if I have a half plane that has this, then that has this, and then that has this, I also should have this point inside, right? And then, so I cannot have this Boolean function, which is one. I mean, let's say I'm using pluses and minuses. So, and then the other case, and when they form a convex polygon, so with four vertices, then the question is which function I cannot realize on this convex polygon. Well, we can just try it. We can
Just, I guess one diagonal from another diagonal you cannot.
So we cannot have plus plus and then minus minus. Well, and how to explain it? Can we give some sort of an argument for that?
Because the diagonal intersect.
That's right, because if there was a half plane that has these 2 points, and but the other half plane has these 2 points, but the problem is that, so it's like this, so I have plus plus minus minus, and then there will be one diagonal, this will be the other diagonal, and they don't intersect, but they have to intersect in a convex polygon. Okay. Then it confirms that at least for d equals 2, the C dimension is 3. But, well, in any case, we can ask what to do for an arbitrary d.
And still for perceptrons.
Yeah. So we want to show that this thing is d plus 1. So we can have a sign of a, well, half. So basically we have indicators of half spaces, right? So I can take a x plus b, where x, so it maps x to 0, 1. And this is from R to the d. Well, maybe at least we can try to understand. So we want to show that we can shatter d plus 1 points. We can realize all functions on some d plus 1 element subset, but we cannot realize them. We cannot do that for d plus 2 points. So maybe at least we can realize, maybe at least we can give an example of, I don't know, d plus 1 points where we can realize everything.
Maybe this should be a simplex. Just as we have a triangle, now we can have a tetrahedron in a three-dimensional space. And of course, it's geometrically clear that if we have one vertex or two vertices, we can split them, cut them from other things.
Yeah, so maybe even like algebraically, I can have maybe a point where all 0 point and then all points like that.
No, it's a bit non-symmetric because one point is special, but okay.
So I can shatter, I mean, I can realize any function because, well, depending on whether I want plus or minus here, I can select b to be, I don't know, plus minus 0.1 maybe, right? And then depending on whether I want plus minus here, I can select A1 to be plus minus 1 so that this number B actually is smaller than this, so it doesn't interfere with A1. So, and if I want plus minus 1 on this point, I will select A2 equal whether I want plus minus 1 and so on. Where I want plus minus here, I can select n equals plus minus 1.
Is it enough to say that any subset of vertices of simplex is a phase? It seems so.
Yes, it's enough to do that, I think. Well, it's better to separate them I mean, better to move it a little bit so that all this h is a strictly positive and all the other nodes are strictly negative, but we can do that if you want.
Of course, because if you have a hyperplane going through some vertices and all other vertices are strictly below this hyperplane, you can shift this hyperplane by epsilon.
Yeah, and then we have
What is more difficult? Why you cannot have more than d plus if we have d plus 2
so
points
let's say I have d plus 2 points.
in RD.
Well, okay, let's try to maybe show that a simpler thing first. Let's say we consider half space, well, just subspaces, right? So without B. So just half spaces that go through 0, right? And we now in that case we have to show that we cannot realize d plus 1. Everything on d plus 1 points. And then basically this actually implies that you cannot realize this basically, it's enough. We can even, I think it's enough to show that you cannot realize everything on d plus 1 points in RD with B equals 0. Why it's enough? Well, I mean, like for half planes without this free coefficient. Because, well, if I can have B, if B might be non-zero, basically I can reduce it to the case when I consider this in dimension d plus 1 and I consider all points. If I can realize anything on d plus 2 points by half planes with where B is not 0, then I can realize everything on these points in a higher dimensional space, d plus 1, by just half spaces without bias. So was it clear? I mean this reduction.
So you
Is it clear
somehow
what is happening?
convert the linear affine subspaces in d dimensions and linear subspaces in d plus 1 dimension. So
Yes.
like you put a plane in a three-dimensional space and then any line of this plane affine is just a plane.
Is a linear subspace, is a linear, like two-dimensional linear subspace, yes.
Yeah.
So now I want to show that I cannot realize anything on d plus 1 points. So my argument should be that I have any d plus 1 points, and I cannot realize anything by the sign of just ax. So Is there any ideas how we should do that? How we use that the dimension of our space is R to the D?
Probably you should use that they are linearly dependent.
Yeah, they are linearly dependent. And let's say this means that some xi plus 1 can be expressed as the previous ones, right? So I can write that xi plus 1 is alpha 1 times x1 plus alpha 2 times x2 times alpha I times xi. Right?
But somehow I guess you should separate positive and negative coefficients as we did in three-dimensional space. We somehow say that a combination of two word in this foregone, we have one diagonal, another diagonal, and we say that the positive combination of one things is equal to the positive combination of other things. No.
Yeah, I mean, then I just, yeah, maybe I just, let me rename these things. If I can. I don't know if I can. So we have B1 times B2 times BI. Basically, an observation is that whatever linear functional I have, well, just by linearity, I have this, right? So I have B1 times AX1 plus, and so on, beta I times AXI. And then the question, I mean, basically why I cannot realize anything, because let's say, well, imagine that all B1, let's say for simplicity first, that all B1, BI are, I don't know, strictly positive. So then what's the problem? Or non-negative, I don't know. What if all these coefficients that express xi plus 1 through x1 and x2 xi, they are all non-negative?
Then you cannot realize when the right hand side functionals are non-negative and left hand side function is negative.
Yes, I cannot realize plus 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 here and then minus here, because if
When
if all
plus
these
is
guys,
non-strict and minus is strict.
yeah. And then basically, if I have to, what I have to change in this argument so that it works in any, for any beta 1, beta I is just when I have, I don't know, some, if B2 is negative, well, if let's say if B1 is negative, then I just have to, I just have to ask this thing to be negative, then this will be non-negative, all this thing will be non-negative, and then this thing cannot be strictly negative. And I can do this for any coefficient which is negative. And then for coefficients that are non-negative, I will ask the function to be non-negative. And for coefficients that are negative, I will ask the function to be strictly negative. And then I cannot obtain here a strictly negative number.
No, it's strange why you separate one coordinate. You just have, if you have 4 points, and there is some combination which may in like we have in a plane, then there is some combination of some of them that is equal to some convex combination of other of them, and so you split things in two parts with positive combination and negative. You take a linear combination that is equal to 0 and just say that one positive linear combination equals another positive linear combination, and this is the splitting.
Yeah, that's true. I mean, it's just you need to somehow argue that this positive. So why there is a Positive. Why the you can why so basically you're trying to say that there is a you can split it in two parts such that convex hull of one part intersect the convex hull of the other part. Right?
Yeah. In this setting, just the cone intersects the other cone because we are now linear, not affine. But okay.
Yeah. Okay. Now from that I can try to deduce an upper bound.
Yeah. All this was just for one
Yeah.
neuron. Yeah.
Yeah, I have 10 minutes and I can try to deduce an upper bound. So now I imagine I have a neural network. I have a neural network with p parameters. With p parameters. So there are some kind of layers going on here, and the total number of parameters is p. So I have to show that the VC dimension is at most of p of log p. P times log p. So how I will show this? I will show the upper bound on this MHN function. So I will show that if I fix n inputs, so I have n inputs from RD to my network, I will show that I can realize at most n plus 1 to the p functions. 1 to the p functions. And this implies, so I will I will lower bound basically, I will upper bound the number of functions that I can realize on n points. It is easy to see that when p is fixed, this function is polynomial in n with the degree of a polynomial which is like the number of parameters. And then it means that infinite, well, at least VC dimension cannot be infinite.
And probably even cannot be large.
Yeah, because if I use this upper bound for my VC dimension, so on one other hand, this thing is 2 to the d, and on the other hand, this is at most d to the p. So it implies that d is at most p times log d, and then some use from this in terms just of p times log p. So is it true?
Because at most p square.
Because let's try. So because d is bounded by I don't know. I don't know. Let's say
We
square
know in
root of
Kolmogorov complexity, but you can write log of lower left-hand side or log of right-hand side in O term, and this is the same.
so let's say square root of d is bounded by d times divided by log p. So this is at most p, and hence d is bounded by p log d, and well, log of d and log square root of d is the same thing up to a constant, so this is O of p log p.
First, it's O of yeah.
So some kind of this annoying argument needed, but we need to show this. Okay, so I have 7 minutes to try to explain this. So what I need to show that, imagine that, okay, I have a neural network. So I have this kind of box here. And I have any n inputs there. Then if I put the first input, and then whatever for any value of parameters, I can put any of these guys there, and I will get an output, and I will get a function, right? I will get a sequence of n zeros and ones. And I need to show that the number of sequences that I can get there is at most n plus 1 to the p. So what I need to show, imagine that I have, this is a space of parameters. This is a space of parameters.
So you have endpoints in RD, yeah?
Yes.
You start with them. Okay.
And then I need to show that my, well, space of parameters, I have all the elements of the matrices and the biases in this neural network. So I need to show that it can be splitted into at most that many parts. So how many parts? N plus 1 to the p parts. Such that any setting of parameters inside one part. So if I fix a point here in the space of parameters, I obtain some function, right? I obtain, in particular, I obtain
some function on inputs. And you want to be the same?
Yeah, I want to show that I split the space of parameters into.
So the sound is very low now, or missing at all. Something is wrong. But you want to split the space of parameters on this path, and every two settings in one part should give the same answer for all inputs for our testing set. And our testing set contains n elements. But we still cannot hear, or it's only me who cannot hear you.
No,
Hello?
I also cannot hear Sasha.
Hello, just very low sound.
I don't know, something happened with my setup.
Can you hear me
to some level?
To some level, we can hear you, yeah.
Okay, let me try to. Okay, to some level.
Yeah.
So we have to show this. But moreover, more strongly, we will show that we can split the space of parameters into n plus 1 to the p parts, such that inside every part, for any of these points, I will obtain the same result on all the neurons, on all the inputs. I mean, basically, well, first of all, I can think of a neural network like that as a function from that takes one of these inputs and returns 0, 1. But more generally, so it's like a function from, in particular, is a function from x1, xn to 0. But you can even think that this is a function that takes one of the inputs and returns, like, in which neurons of the network you have 0 or 1s. So if you have S neurons.
So it's a more detailed function. So even those functions will be the same in each of the parts.
Yeah, we will show that even those functions will be the same in each of the parts. And how we will show this? We will show this by induction on the neurons. So we will add neurons one by one. And And we will have parts where inside each of the parts, the neural network gives the same result. If I give it xi, it will give the same result for xi up to neurons of some index for any setting of the parameter inside the part. And then I add a new neuron, and I have to show that it splits in at most my current part in at most n+1 to the p parts. I don't know, let's say pk, where the pk is the number of parameters of my neuron.
Yeah.
Why is that? Now I will use an upper bound on VC dimension for perceptrons, right? So because I have a neuron k, and then I have a space of parameters, and I'm inside the part where everything is just fixed by the input, right? So if I have xi, I know what I will have in all the neurons before k, independently of what are the parameters here. So I just give it xi, and I know what will be happening in the network up to neuron k, right? And I have this for every input, x1, xa, xi, xn. And then here, this guy has some number of parameters. So it calculates a linear combination of some previous neurons, some kind of linear combination of, I don't know how many neurons. I don't know, let's say A1 times Y1 plus AT times YT plus B.
So you consider neurons going from input layer to output layers, yeah? So you add a neuron on the last layer.
It could be any neuron on one of the layers. So, but it receives on input some neurons from the previous layers for which we can assume that like already they are like functions of just xi, right?
Yeah.
So it receives on input t neurons y1, yt. It has t+1 parameters a1, a2, at, b. And we have to show that it splits my current part of the parameter space in at most n+1 to the t+1 parts. But I mean, really you have to show that, okay, like for input x1, everything is fixed in the network, and then there is some fixed input to the neuron k for x1. Then for x2, there is some other fixed input to the neuron. For xn, there is some other fixed input to the neuron. And then by choosing different values of parameters a1, at, b, you can obtain different functions for x1, for x2, for xn. You can basically obtain different sequences of zeros and ones. But how many different sequences you can obtain? I'm claiming now you can use Sauer-Schellach lemma because the VC dimension of this stuff, of just this neuron, if you consider y1, y1, yt as inputs, is just is t+1, sorry, because there are t+1 parameters, right?
So we see the mention of so how many different?
Yeah, so basically you fixed x1, so you fixed parameters so that all the neurons up to neuron number k have fixed values just depending on the input. then basically you
Yeah.
have n different inputs to that perceptron, to this neuron that computes a perceptron. The question is how many different functions you can realize now on this n inputs. Well, at most, that many that tells at most that many is given by the Sauer-Shelach lemma, which is the sum of binomials up to like, so it will be n 0 plus n times t plus 1, but it's easier to bound this by n plus 1 to the t plus 1, right? And then basically when you take the product of all these things for all the neurons, you have the product of n plus 1, and then in exponents you have the number of weights of each, of the number of parameters for each neurons. But if you sum up these things, all these things, you will obtain just the total number of parameters in the network. So, yeah.
Yeah, okay. I think I need to think again, but it's clear what you are trying to do and why. And one should just check and think again whether it's indeed our Sherlock can be applied. So the plan is clear, but I need more time to be convinced.
Yeah, but I guess I'll stop here.
Yeah, and just maybe you can say so it's kind of classical results. And are there some modern things what people are doing now in this domain? Or this is well established and just everyone enjoys it and does nothing special?
I mean, this is so-called, I think it's kind of obscure area in any case. Like, I mean, people are using some kind of this technology to prove, well, I guess obscure people like me, for example, or to prove something, to prove some kind of lower bounds for transformers, let's say, some kind of this stuff. But regarding, I mean, so if you ask, so basically it's not very an active area of research. So like to obtain exact upper bounds on the VC dimension of some kind of neural networks with some kind of activation functions, there is sort of not we don't know exactly what's happening with ReLU. As I said, there was some kind of relatively recent result about that, but I mean it's just, I don't know, an open problem that, I don't know, you can publish maybe in some conference, but it's not will be some kind of groundbreaking thing. The other thing is that people are now doing, also trying to use this kind of upper bounds on VC dimension to show that something is not doable. Basically for lower bounds, for some kind of neural networks, some kind of transformers, where you use this kind of upper bounds on VC dimension.
Yeah. Okay. So it's kind of useful thing for learning, even if we don't know what it is useful for. Yeah.
No, I mean, intuitively, like philosophically, you can say, okay, you have this kind of class of neural networks, and I don't know, if you have some real world task, okay, you know that, I don't know, like to classify cats from dogs. And then somehow there is an idea, so there exists a neural network that does it well. We don't know which one, but okay, how to find the weights of a neural network, that parameters of the neural network that does it? Well, we can try to learn. We can try to optimize it on a data set, right? To find the setting of parameters where on some given data set, it classifies, it distinguishes dogs from cats very well. But then you are asked to expect, well, will it be working good for examples outside the data set? And then, well, the theory tells you that if VC dimension is not very big, then and you trained it on a relatively, I mean, if you train it on sufficiently large data set, not very big, like polynomial size, then it also will be very good outside the data set. So like philosophically, it's clear. Like on one hand, there is a belief. So if you have some kind of task, like distinguishes cats of dogs, there exists a neural network that does it relatively good. And then if it has a low VC dimension, it also generalizes good. So some kind of having this kind of result should be, I don't know, useful or should explain something. But of course, nobody is interested in this. They just train it and just look what's happening.
Yeah, okay. No, okay. That's maybe you should
Well,
explain
maybe
sometimes
Kudryshov
again.
will kind of
No,
say
Kudryshov will
different
speak about different things definitely. But in any way, if someone,
But I mean, there was a question to Kudryshov whether the classic results of machine learning theorem were were useful for
yeah, do
in
they
the
need
more
to learn
developed
all this to
deep learning.
for making a perfect chat GPT that answers questions miraculously well?
Yeah.
Okay.
More interesting if we can build up a ChatGPT which can verify arguments, not found new arguments, not no new proofs, but verify existing proofs. It's much more interesting question because there are a lot of people who can invent new proofs, and very few people can verify them. It's the most important question to any people who does work in artificial intelligence.
No, it's just what you mean by verifying. So it should always verify correctly.
Checking correctness the proof.
No, but imagine
Take
there
a
is
proof MIP star equals recursive enumerative languages. How many people can verify it?
no. If it say I believe it, it's okay or what? What it should say?
No, correctness of mathematical proof.
No, so if a person just reads the paper and says I understand that, I can explain it to you. That's paper. The proof is okay. Do we agree that this person verified the proof? It's not clear how you understand the notion of verification.
It's a good question, of course, but it's a very simple test. You can supply this person a wrong proof, and you know in what place there is a mistake.
Yeah.
And if the person says that, well, the proof is okay, then you should not trust it. If on some simple proofs a person says some reasonable things, then you can trust this person.
No, I think that this
Cases.
current ChatGPT is somehow doing something like this for simple proofs, but of course it also says some nonsense in other cases. But so it's not that easy to say what we want. But actually, what I think, what probably Yura will say us something about the technology that you convert your so you translate your question, your theorem in some formal system, maybe by hand or whatever, and then you ask the system to read the informal proof and try to provide a formal proof in the system. And maybe it can do this at some extent, but we should ask.
Yeah, maybe their systems can do that, but in general.
So, Sasha, is it correct to understand you that there are existing programs which can translate papers on archive to formal systems, say COX or something like other formal system.
No, I guess that first of all, not all papers on archive, but I guess that there are some humans who can translate simple arguments from textbooks to formal systems. And I guess that to some extent, this activity can be also simulated by ChatGPT systems. But
in simple cases.
Yeah, for human and also in simple cases. So
no, human can do much better. Yuri Matyasevich and 6 students from Bremen verified the proof of 10th Hilbert problem. They translated the Matyasevich proof to formal system and verified them by using computers.
No, first of all, even the translation itself, it needs to be checked by someone external before. No, but of course, but the human are becoming better and better, and I guess that now, at least now, the ChatGPT is behind. But looking at what it does in other cases, it's difficult to be sure that it will be behind.
What I have about ChatGPT and all that stuff, they are completely non-interesting in verifying proofs. They're interesting to solve some intricate problems like Olympiad problems and that stuff.
I mean, verifying proofs in a natural language.
Yeah, of course. You can just take a textbook for calculus or for graph theory and verify them. It is the first step.
Okay.
The second step, you can take.
Okay, if you are, let's make an experiment which is quite easy. Just write a half-page wrong proof of something, and let's see what it will say. Okay?
It's a very easy experiment because you can take almost random proof from a book and it will contain a small mistake anyway.
No, but a small, no, it's not fair. You should compare it with what a human will say about this proof. And most humans will say that the proof is okay, even there are some misprint or something. So I guess you should make a significant error. So a human will not approve it. And then it's interesting to see what will say the ChatGPT. So
there are examples, but rather complicated theorems which consider it true during 50 years and then
yeah. But let's start with something simple. No, I don't know. You have a student who submitted wrong proofs. Just type one of them, and which is really wrong, not some indexes wrong.
I see.
And just let's try what they say. Just say that a student submitted the proof for this problem and proof. And can you say whether it's correct or not? What will be?
Student can be substituted by ChatGPT because ChatGPT generally provides wrong proofs.
Okay, but just try to prevent a test case yourself to see before using the ChatGPT and then see what is happening.
Sorry,
it's just like
who should read this text? I don't understand.
No, you write some text, which is a wrong proof or right proof, or maybe two texts, which one is wrong and the other is true. And then you send it to other participant of the seminar. And the participant of the seminar will read it and will say which of the texts is true or whether...
I have hundreds of solutions by students and many of them are wrong.
Okay.
Send it to
don't do it with hundreds
seminars members and
I
think that
don't do it with hundreds things. Take one, two or three of them and just preferably not very long, and just let's send it to us, and also we will try to send it to ChatGPT and compare the results. Just write something half page of a good proof and half page of a bad proof. And you can use your students' submissions, of course, if you want. But it's good if you know which is right and which is not. So we can compare it with the ground truth with what we found by ourselves and by our programs.
So you are sure that ChatGPT can find
No, I am not sure at all.
student mistakes?
No, I'm not sure at all. I think it's an interesting experiment, which is easy
why
to do.
I should do it? There are people who makes professional research in this area, and why they did not provide these experiments? My question is that.
No, I guess I
No,
guess
no,
they
I mean,
did.
I can give you a kind of experiments that we did, for example. We asked,
Can you provide a reference to results of these experiments?
yes, I can give you a reference to on our paper in archive, but not exactly this. We, for example, we did an experiment where there was a correct Python code, and then was just
No, not Python code. Forget about Python code. I am saying about mathematical proofs.
Okay.
It's completely different situation.
Okay.
That it's a very expensive thing to do. Where I will get you 100 proofs of mathematical.
No, just don't. Okay, no. If Misha doesn't want this, it's a bit strange to me because you say I don't believe that the beer can drive a bicycle, and then I'm saying let's try, let's bring a bicycle to the zoo. And
No. If you have references about defined mathematical proofs by chatbots, models, okay, I would happy to get such references. I do not know anything.
Okay, but why do
the question about the direction?
Okay, if you don't want to do this, I'll try to do this myself, maybe, and will next time try to say what is the. It would be more clean if you try it, but if you aren't ready to invest your time in this, I will try to do this myself. Okay, so next time we will have what?
Well, next
Sasha.
time what?
I guess 22nd of September we will have some talk, yeah?
We will have, well, the idea is to have Arturo Merino, who is a researcher in one of the institutes in Chile, who works in combinatorial optimization, and then he will tell if should explain a theorem that I have a 0-1 polyhedron, then it has a Hamiltonian path over edges.
So what is 0-1 polyhedron?
It's a polyhedron where all the vertices
are just subset of Boolean cube.
No, I mean, it's not set because it's basically...
No, vertices of Boolean cube.
Vertices, yeah, but edges are not necessarily edges of...
Yeah. So you just take some vertices of Boolean cube
take a convex column
of something, and then you say that always has a Hamiltonian path. And
yes, it seems that the result was known for a time. I've heard about it.
Yeah, and
10 years ago, maybe.
Sorry?
Yeah. So he explained a new proof or just the old proof or whatever.
Yeah, new simpler proof of this.
Okay. It's very interesting.
He has also a result, something that you can sort of in polynomial time enumerate this path under some assumptions about this polyhedron, and then you can use it to polynomially enumerate some combinatorial objects.
So sorry, all set of Hamiltonian paths can be generated by, in some assumption, maybe
no, you can
incremental.
you can generate this Hamiltonian path with a how they call it, polynomial waiting time.
I suppose incrementation
algorithm. Incremented time.
Yeah.
So, for example, it will imply that you can generate all matchings in the graph or something like that in polynomial incrementation time.
Yeah, I see. So they can generate Hamiltonian paths incrementally for any 0-1 polyhedron.
Polyhedron, which is given, well, it should given be some kind of explicitly or something. You should have some kind of assumption about this polyhedron. I don't know, that you can solve a linear problem.
Yes, we have a problem because there are many vertices of this polyhedron. How we
How we give
define?
it. Well, I
Yeah,
mean, I
yeah.
think it has a result that if you can solve linear programming in polynomial time for this polyhedron, then it's enough.
I see.
So that would
Okay.
Say
mean
for,
then on 29, we guess maybe we'll have Kudryshov.
Yeah,
Nothing
I will
time, right?
speak
Because
with him
Shane is
today. Maybe try to agree on 29.
Yeah, and then we can also have somebody from the place where I work who will explain in more detail how ChatGPT works technically, and who can program it and so on, depending on what happens with Kudryshov.
Okay. If Kudryshov is still alive after the talk, then we can try another guy. Okay. Okay.
Okay, bye.
Fantastic. Yeah.
bye.
Bye.